Displacement ventilation divide. It is a room air distribution strategy where conditioned outdoor air is supplied at a low velocity from air supply diffusers located near floor level and extracted above the occupied zone, usually at ceiling height. A typical displacement ventilation system, such as one in an office space, supplies conditioned cold air from an air handling unit (IU) through a low induction air diffuser. Diffuser types vary by applications. Diffusers can be located against a wall-mounted, at the corner of a room, corner-mounted, or above the floor but not against a wall, freestanding. The cool air accelerates because of the buoyancy force, spreads in a thin layer over the floor, reaching a relatively high velocity before rising due to heat exchange with heat sources, for example, occupants, computers, lights. Absorbing the heat from heat sources, the cold air becomes warmer and less dense. The density difference between cold air and warm air creates upward convective flows known as thermal plumes. Instead of working as a standalone system in interior space, displacement ventilation system can also be coupled with other cooling and heating sources, such as radiant chilled ceilings or baseboard heating. Displacement ventilation has been applied in many famous buildings such as the Suvarnabhumi International Airport in Bangkok, Thailand, the NASA Jet Propulsion Laboratory Flight Projects Center building, and the San Francisco International Airport Terminal 2 among other applications. Displacement ventilation systems are quieter than conventional overhead systems with better ventilation efficiency. Hence, it could enhance indoor air quality and provide desirable acoustic environment. Displacement ventilation systems are appropriate in space where high ventilation is required, such as classrooms, conference rooms, and offices. Displacement ventilation can be a cause of discomfort due to the large vertical temperature gradient and drafts. According to Melikov and Pechurov's research, sensations of cold caused by vertical temperature difference and draft are usually occurred at the lower leg/ankle/feet region, while warm sensations at the head are reported. The research also indicates that the draft rating model could predict the draft risk with good accuracy in rooms with displacement ventilation systems. There is a trade-off inherent in these two issues. By increasing the flow rate and the ability to remove greater thermal loads, the vertical temperature gradient can be reduced, but this could increase the risk of drafts. Pairing displacement ventilation with radiant chilled ceilings is an effort to mitigate this problem. According to some studies, displacement ventilation systems can only provide acceptable comfort if the corresponding cooling load is less than about 13 2/HSF or 40 W/square meters. One benefit of displacement ventilation is possibly the superior indoor air quality achieved with exhausting contaminated air out of the room. Better air quality is achieved when the pollution source is also a heat source. Some studies have demonstrated that displacement ventilation may save energy as compared to standard mixing ventilation, depending on the use type of the building, design/massing/orientation, and other factors. However, for the evaluation of energy consumption of displacement ventilation, the numerical simulation is the main method, since yearly measurements are too expensive and time-consuming. Hence, whether displacement ventilation could help with saving energy is still debated. In general, displacement ventilation is attractive to the core region in a building since no heating is needed. However, the perimeter zones require high cooling energy,